The next presentation we have by the speaker, that is Mr. Vinayak Nagpal, who is the CEO of Zendar. Let me brief about our speaker. Vinayak co-founded Zendar in 2017 to develop advanced imaging radars for autonomous systems. Previously, he worked on radio astronomy instrumentation, contributing to the first sub-millimeter images of the Milky Way central black hole. He holds a PhD in electrical engineering from UC Berkeley and has conducted research at Harvard Smithsonian Center for Astrophysics and Nokia Bell Labs. So I'm requesting Mr. Vinayak Nagpal, CEO Zendar.
Thank you. Can we put up the slides? Okay, I'm going to talk a little bit about ADAS in India, which everyone else is talking about. The biggest question that everyone has on their mind is, why is ADAS not so prevalent in India? Like, most of the cars don't have any ADAS. Even if they do have some ADAS, nobody uses it. Why is that the case? Answer is pretty simple. ADAS doesn't really work in India today, and it costs too much money. Why doesn't it work? Like, everybody who has used an ADAS system in India can tell you, the first thing you will switch off is the lane keep assist system, because it forces you to stay in the lane, but nobody else is staying in the lane, so you kind of have to turn that off. Then you start turning off the collision warning system because it's beeping all the time. Then you have to turn off the AEB system because the AEB is braking for all the speed breakers and is braking randomly in places, so that's not very useful. ACC, people would love to use ACC on Indian roads, but it's so limited that it only works at certain speeds. It can't handle pedestrians. It can't handle two-wheelers. And you're constantly turning ACC on and off. It's taking more work to actually run the ACC system than it's to drive, so you stop using it. And to get all these features, you're paying 1.5 lakh rupees extra on your car. So the whole thing is not making a lot of sense. And so how do we fix this? To fix this, we need ADAS that actually works and is quite cheap. And so I'm going to talk about how we solve these two problems. So first, let's start with how to make it really cheap, because this is still a lot of money for the Indian market. When you think about how to make it cheap, the first thing you want to ask is, what is the most expensive thing that you want to make cheap? So in an ADAS system, what is on the road today, you have cameras and radars and you have some processors. What's the most expensive part? It turns out the most expensive thing is not the camera. The camera is pretty cheap. The radar is also pretty cheap. It's the processor. It's the SoC that is doing all the processing with camera and radar. It's costing about 30,000 rupees. It's the most expensive piece in there. And why is it so expensive? It is expensive because it's doing a lot of computation. It's doing about 100 tera operations per second. Why does it need 100 tera operations per second? Because the whole system is very camera-centric. What do I mean by camera-centric? So the ADAS system, most of the things are being done by the camera. So the camera is doing the object detection. It's doing the classification. Is that a person? Is that a car? The camera is also looking at traffic lights. It's looking at lane markings, drivable area. The radar is doing very little things. It's doing like, hey, what's the distance to the object? How fast is the car moving? So, okay, most of the compute is going to all this camera processing. So how do we make it cheaper? Turns out, if you change the architecture a little bit, you can make this thing 10 times cheaper. And I'll tell you why. So what we did is we moved the roles of camera and radar around a little bit. So instead of using the camera for everything, which tends to be expensive, you do more with the radar. So you do object detection with the radar. You also can classify objects with radar, with this, and you can find out where you can drive with the radar. And you use the camera just for traffic lights and lanes. Now, if you do it this way, the whole compute that is needed falls down to about 5 tera operations per second. So that's a 20x reduction in the compute and almost a 10x reduction in the cost. And somebody might ask, why is that the case? It's because camera systems are naturally more expensive to do computation. So you have to learn so many colors. You have to learn so many light conditions. You also have to estimate how far things are. Whereas in a radar world, No colors matter. Distances are measured natively, and velocities measured natively. So the processing needed for a radar-centric system is just naturally less. The next question you'll ask is, well, if it's so much cheaper, why doesn't everyone do this? Well, turns out, for a long time, radar technology just wasn't very good enough for doing complete semantic scene understanding and actually classifying objects, recognizing objects. But that has changed. It's changed drastically today. Today, you can do complete scene understanding with the radar, and I'll show you that it actually works. Here's just an urban scene in Berkeley where our office is, and you'll see here there's a bunch of pedestrians. On the bottom left is a bird's eye view of what the radar is seeing, and on the bottom right is a 3D view of it. All those little icons are pedestrians, and the cars are the boxes. And the camera is just for reference. So everything that you see is done just with the radar. And you see it's pretty impressive in terms of recognizing all the stationary objects, how far they are, how big they are, where all the pedestrians are. And this is a state-of-the-art AI-capable radar, which is very cheap and is also fairly cheap on a compute standpoint. I'll let this video play. It's got a lot going on. It's pretty interesting to see how much detail, both of how far something is, what it is being captured. You'll also see a scooter pass by, which will be denoted by a different box. There's the scooter. It has a slightly different box. So you get an idea that you can do a lot with radar, and if you do a lot with radar, you can make the system a lot cheaper, like 10 times cheaper. And that's a big deal. Like if you want to bring ADAS in India, making it 10 times cheaper is a big deal. Well, there was two problems I talked about. It has to be cheap, and it has to actually work. So I want to switch gears and talk about what is important to make the system actually work. So if you look today, all the ADAS systems that you use, so think of adaptive cruise control as an example. It's based on this left view. It's based on a rules-based system. So you have some sensors. The sensors make some environmental model. And from the environment model, you make some policy about how to drive. And it's based on some rules. So ACC is like, I have to find a lead vehicle. If the lead vehicle is going at a certain speed, I match my speed with that. It's a bunch of if-then statements. And all these rules-based systems were developed for American and European highways, and they work very well over there. And many suppliers brought these systems to India, and they tried to make them work, and they don't work. And then they said, okay, let's change these rules, and everyone tried to modify the rules, and it still didn't work. And the reason is the Indian road conditions are just fundamentally far more chaotic, that no set of rules seem to work. And so you make any rules-based system, it's just never going to work. And so in order to change that, we're making an AI-learned-based system. So you don't make a driving function based on rules. You make it based on an AI model. And the AI model learns from an actual driver in actual road conditions in India and how other drivers behave and how a human would respond to the other behaviors. And so you build a driving function based with that approach. And so if you see, an AI-based driving function also has a real-world feedback loop. So you deploy an AI-based ACC function on the road, and people are using it. And every time the ACC does something wrong and the driver disengages it, you capture that little chunk of data, and you send it back, and you feed it back to your AI model, say, hey, improve your performance on that scenario. And it keeps getting better with time. And so this is not some abstract idea. It actually works today. And so here I'll show you an ACC function that is completely end-to-end AI-based. So over here, it's in a highway. It's in California, but it's identifying the lead vehicle that you have to track in the blue box. And as the driving condition changes, so you change lanes or somebody cuts in front of you, the AI immediately figures out which is the lead vehicle, whose speed I have to match. And you might have seen ACC systems, but the beauty here is it's a fully AI-based system. And adapting this to India means you have to just train the model with data from India rather than have to go and fight with the rules that other people had made for Europe. So anyway, that talks about the two things I wanted to focus on, how to make these systems actually work and how to make them cheap. And I'll end a little bit talking about Zendar. We are a company based in Berkeley. We started about 8 years ago. we started building advanced AI-based radars. And today, we are bringing this technology to India, and we provide a complete reference hardware systems for all the hardware you need, the radars, the cameras, the compute systems. We provide AI perception models, and we are training these AI perception models with real-world data in India as we speak. And we also provide an end-to-end ADAS software stack. We partner with NXP for all the silicon solutions. All our solutions are built on NXP silicon. And that's all I want to talk about. It's Zendar. And so we are bringing new ADAS technology to India. And the goal is two things: to make it really cheap and to make it actually work. Yeah, any questions?
Hello. Okay, thank you for the wonderful.
I can't hear you.
Can you hear me now?
Yes.
Thank you for the wonderful session. So I have this question on the AI solution. So basically, so you are using AI model to. Okay. So basically, you are passing the radar output to the AI model. So again, you have to inference the output of the sensor data. So again, it takes a lot of computation power. So again, the hardware cost would shoot up, right?
No, so what we are doing is, I think traditionally radar systems throw away a lot of the data. They kind of compute what is called a point cloud. The point cloud throws away most of the information, so you can't do much with that information. So what we have done is, right from the RF spectrum that comes off the antenna to the driving function is an end-to-end AI model. And that AI model we have shown is about 2 orders of magnitude less compute than an equivalent camera-centric system. So all our systems fit within 3 to 5 TOPS. You can get a complete L2 system within about 5 tera operations per second of compute. That can fit into a $25, $30 SoC. So that's a huge reduction in cost. Already, the camera-based systems do the same thing. They do it with AI as well, but it just takes a lot more compute when you do it with camera.
Okay.
Hi. Okay, I just wanted to understand, like, what are your challenges with respect to data collection? For example, a lot of countries have their own restrictions in terms of collecting data from one region and using it in another, or using it for training their own models outside the country. So what are the challenges you face here?
So I think the biggest challenge is none of the data we have from the US is very useful here. So you have to start with local data. Just the objects are completely different. They are driving on the opposite side of the road. There's rickshaws. The shapes of the vehicles are completely different than what you see in Western countries. So your model has to learn all that, and it has to work with local data. And so from the ground up, we are building our system with local data. And also the driving function is based on driving on the road, like how a driver behaves on the road. The ACC system has to mimic that. And so even that data is local.